Hi guys, we're going to be doing some review questions to prepare for the quiz on arithmetic and geometric sequences with some compound interest questions as well. So let's look at number one. A woman deposits $100 into her son's savings account on his first birthday. So I'm just going to write that down. So we've got his first birthday. And she deposited $100. On his second birthday, she's deposited $125. On the third birthday, she's deposited $150, and so on. Now I think you can already see the pattern. What are we doing to each term in order to get to the next term? Pretty clear that I'm adding 25. Every single time that is the rule. That makes this an arithmetic sequence where our common difference is equal to 25. Now if you think of the first birthday as U1, and the second birthday as U2, and the third birthday as U3, well then we can see that U1 is equal to 100. And so that's a useful piece of information as well. We now know the value of U1 and the value of D. Furthermore, you might notice that in order to get U3, the third birthday, we had to take the original value and add 2 of the common differences. That is to say, for the third birthday, 1 less than 3 of the common differences. In general here, we're dealing with an arithmetic sequence such that on the nth birthday, however old he is, he earned the original $100 plus n minus 1 increments of $25. So that's kind of a way of thinking about the nth term. We're being asked specifically how much was deposited on his 17th birthday. And so that's going to be then 17th birthday, or U17, will be equal to the original $100 deposit, which has gone up 16 times. That is 1 less than 17 times 25. And if we resolve that, we get 100 plus 400, and the deposit on his 17th birthday is $500. Okay, so that's the answer to number 1. Number 2. The population of Bangor is growing each year. At the end of 1996, the population was 40,000. Now it doesn't tell me what 1997's population was, but it does tell me 1998 that the population is now 44,100. It says that the annual figures follow a geometric progression, meaning that in order to get from one term to the next, I always have to multiply by r. So it's pretty clear then that in order to get from 40,000 to 44,100, I took my 40,000 and I multiplied it by r and then by r again. And that is what gave me the 44,100. So now I can solve for r. Let's divide both sides of this equation by 40,000 to get our r squared alone. This means that r squared will be equal to I think I'm going to have to do this on the calculator. 44,100 divided by 40,000. 1.10. Oops, okay. Let's change that. 1.1025. So let's isolate now for r. That means that we're taking the square root of both sides. Don't forget that when you take the square root of both sides, we need to add a plus minus. And so r, when we take the square root of this value, let's say take the square root of the answer that we just had on the previous step. So you can call up the answer from the previous step with second negative. And that will take the square root, in this case, of the answer that I had just found. And that equals 1.05. Now hang on though. How could r be equal to a negative value? If r was negative, then I'd be multiplying 40,000 by a negative 1.05, and 40,000 times a negative 1.05 gives me a population of negative 42,000. Well, that's of course impossible to have a negative population. So it turns out that we can throw out this negative answer of r just because in this particular problem it doesn't make sense in context. And so then by throwing out the negative, we could say therefore r is equal to only positive 1.05. So now let's actually get to the question. What is the population of Bangor at the end of 1997? So for 1997, which you can think of, I suppose, as your U2, how do we get U2 in a geometric progression? Well, we're going to take our U1 and we're going to multiply it by r. So in our case, that's going to be 40,000 times 1.05. And, well, I already did that here, didn't I? I just have to ignore the negative. And so I get an answer then of 42,000. And now we know that for 1997, the population was 42,000. Part B asks us to find the population of Bangor at the end of 1992. Now that's 4 years before 1996. So if you think that in here, year 2, or year 1997, but 1 year afterwards, we had multiplied by one of the instances of r. And in this term, we had multiplied by r squared because it's 2 years in the future. I guess for U4, it's going to be 3 years in the future, so you'll take your 40,000 and multiply by r 3 times, which means r cubed. So what about moving 4 years in the past? Well, it turns out that in 1992, we can figure out the answer. It would be U1 times r to the negative 4, because we're moving 4 years earlier than the 1996. And so there's the 1996 population of 40,000. I need to multiply by the growth rate, but it's being taken to the power of negative 4 because we're moving 4 years into the past. So then 40,000 times 1.05 raised to the power of negative 4 gives me an answer of 32,908. And of course I don't want to include any decimal places because these are people. You can't have a decimal person. And you could round this if you liked, although it's not necessary, to 3 significant figures, 32,900. Another approach you could have taken to solving this problem would have been to reset your U1 term as 1992. And so our let's see, that would mean that 1996, let's just think about this then, 1992, 1993, 1994, 1995, and then 1996, we know that we've got 40,000 people. So to get from 1992 to 1996, if we're multiplying by r every time, we can conclude then that our U1 value, our 1992 population, has got to be multiplied by r to the power of 4 in order to get our, in fact, yeah, we know what r is, don't we? So let's substitute straight away. We're multiplying, we're multiplying by 1.05 to the power of 4. And we know that this amount equals our population 4 years later in 1996 of 40,000. So in order to solve for U1, we just have to divide both sides by this amount, and we'll have U1 alone. So it'll be 40,000 divided by 1.05 to the power of 4. Let's do that. 40,000, our 1996 population, divided by 1.05 to the power of 4. And look, you get the exact same answer as we found using the negative 4 method. So 32,908 is the number of people. Number 3. Moranti deposits $1,000 into an investment account that pays 5% interest per annum. Clearly this is a compound interest problem, so let's write down the new compound interest formula. Our future value of some money is going to be equal to the original or the current value of the money, which is then being acted on by a growth rate of 1 plus our interest rate, 5%. And then I've also got, well, how many times am I compounding each year? It just says annually, so I'm only compounding once a year. And so it's only a 1 which is being multiplied by the number of years. Oh, I said I would write down the full formula and I forgot to do that, so I'm going to just back up a little bit. There we go. Let's do that again. So the formula was 1 plus r over 100k, where k is the number of times we're compounding each year, and then to the power of kn, where n is the number of years. Now let's substitute into the formula. It says what will be the value of the investment, so I'm looking for the future value. Our current value, the original deposit or the principal, is 1,000. We've got 5%, there's my 5 over 100 representing 5%. I'm only compounding once a year, so k is equal to 1, and I'm doing this for 5 years. So let's type this into the calculator then. 1,000 times 1 plus 5 divided by... Now here we have to be very careful, because I need to put this denominator, 100 times 1, into parentheses, in order to ensure that it is dividing by this entire denominator. And then I'm raising this result, so I'll close the other set of parentheses. Oops, that's not what I meant. There we go. I'm raising this result all to the power of 1 times 5. And we get an answer of 1,276. This is dollars, so you include the units, 1,276. And we always use 2 decimal places when working with money, although you do have the option of rounding to the nearest dollar, or even to 3 significant figures. So any of these 3 answers would be accepted. That was part A. What about part B? How many years would it take for Moranti's investment of 1,000 to double in value? So the future value of her original 1,000 investment, which has been doubled, is now 2,000. The original or current value is 1,000. I know that I've got a 5% interest rate. I'm not going to bother writing down the 1 because of course it won't change the value. And all to the power of n, where n represents the number of years that it's going to take. Now please note that in this problem, because she's only being paid interest each year, she needs to wait until the end of a year in order for the interest to finally kick in and for her account balance to go upwards. So because we're looking for the end of a year, that is to say the number of complete years that have passed, we know that n must be an integer. This is an important observation because it gives us a clue about the solution technique that we can use. I'm going to use a table, and it's always good to use a table when you're looking for an integer answer. So let's start by going to y equals and putting in the right-hand side here. That's going to be 1,000 times 1 plus 5 over 100. So that's my 5% increase, being raised to the power of, well, I can't use an n, so I'll use an x. And there I've put in the function. Now I'm going to say second graph to access the table. And you'll see that when I've met 0 years have passed, I'm still at my original amount of 1,000. After 1 year, my 5% interest rate has grown my money to 1,050, and so forth. Well, let's keep scrolling down and find out when I have finally passed $2,000. There we go. So we'll see then that if we put in, let me put it in a full solution here. So we state that y1 is equal to our function of 1,000 times 1 plus 5% to the power of x. And now we'll draw a little picture of our table. We don't need to use the whole table. We just need to show the values that matter. We first need to show the row where we have not quite reached 2,000. And so we're at 1,979.9. But when we get to the 15th year, finally, with the end of the year interest kicking in and being added to her balance, she's now finally beaten 2,000 $2,000 and her money is finally doubled, and therefore the answer is 15 years. Another way you could have done this problem, though, if you hadn't recognized immediately that you needed to have an integer answer, would have been to go to the graph. So I've already put in one side of my equation, my right-hand side. Let's now put in the left-hand side of the equation, 2,000. And this is going to create two different lines, or two different curves. I want to find out where they are equal to each other. In other words, where do they intersect? Before I graph, I'm going to need to adjust my window, because I know that 2,000 is a constant value at 2,000, and so I need to change my y max to be 2,000 so that I can see that line. Let's make it a little bit bigger, like 2,100. I also know that there's no point having negative values of x, because she's starting at 1,000 at year 0, and her money's growing. But I will make my x max something like 20, because maybe it will take more than 10 years for it to double in value. Now let's look at the graph. Here's our curved function. This is her money that's growing. And then there's the $2,000 that she wants it to grow up to. And the intersection between these two curves will represent the number of years that it took for that money to grow. So we'll say second trace. In order to access the calculate menu, we'll come down to option 5, intersect. Yes, this is our first curve, so we'll press enter. Yes, the 2,000 is the other side of the equation, so we'll press enter. And then we'll move the cursor fairly close to that intersection point. And then we'll press enter as our guess. And it tells us that the value of x, because we're only looking for an x in this problem, right? The y is not really very relevant. The x is 14.2 if we round to 3 significant figures. So how would I show my work if I'm using the graphing technique? Just with a quick sketch. Here's the 2,000, and here's the 1,000 value that was rising. And this is your intersection point, which occurs at 14.2, 2,000. And so then we could say then that means that, oops, it's an x, isn't it? So that means then that n, we figured out, was 14.2. However, now we realize that she's only getting the money at the end of the year. So when we reach 14 years, we know that she doesn't have enough. At 14.2 years, her balance is still remaining the same until the end of that year, at which point the interest will finally kick in. So in fact, we have to round up to 15. That's actually not rounding, is it? It's just moving up to the next integer when finally her money will kick in and she'll have more than $2,000 and her money will have doubled. So 15 years is your answer. Let's go on now to number 4. Mr. Jones decides to increase the amount of money he spends on food by D pounds every year. In the first year, he spends A pounds. Alright, let's write this down. So in year 1, he spent A. You can think of this as your first term. U2, that's of course going to be the amount he spent in year 2. It tells us that he spent D, let me just say this again, he increased the amount of money he spent by D. And so it's going to be A plus D. That's the increase of D pounds. The third term, representing the amount that he spent on food in year 3, well, he's had to take the amount that he spent in year 2 and then increase it by D, because he increases by D every year. Or you might express this, in fact, as A plus 2D. Let's write out one more term, just to make sure we can see the pattern. U4, representing year 4. His A plus 2D from the previous year has now been increased by another D pounds. This means that he's got A plus 3D. At this stage, you should be able to see the pattern. In year 4, we did A plus 3D. In year 3, we did A plus 2D. So let's generalize. In year n, we can presume then that the coefficient of D is always 1 less, and so we'll have A plus n minus 1D. Now the question goes on and tells us that in the 8th year, so that's U8, he spent twice as much as in the 4th year, U4. So 2 times U4. Let's now substitute. U8 we know is going to be A, the original expenditure, plus 7D, because it's always one less. And that's going to be equal to 2 times A plus, for U4, so 3D. Let's simplify this a little bit. A plus 7D equals 2A plus 6D, right, if the 2 distributes. And lastly then, if I bring everything to the left-hand side of the equation, then I'll find that A minus 2A, and then I've got 7D, and I bring the 6D across, it becomes a negative 6D, and I'll simplify and I get negative A plus D is equal to 0. So far so good. I've also been told that in the 20th year, he spent 4,000 British pounds. So let's think about what we're saying here. In the 20th year, he spent... Now let's think about what the 20th year is, right? That's going to be the original term plus 19D. And so that must mean then that if he spent 4,000 pounds, that we've got another equation that we can use. A plus 19D is equal to 4,000 pounds. Well, check out these two equations that we've written. They're all perfectly ready for us to use Poly-Samilt. So we'll go into Poly-Samilt 2. In this case, we're solving some simultaneous equations. There are two equations with two unknowns. And let's put in the coefficients. So we have a negative 1 in front of the A, a 1 in front of the D, and then a 0. And then we have a 1 in front of the A, a 19 in front of the D, and a 4,000 on the right-hand side. And now let's press solve, and we'll see that both A and D are equal to 200. Turns out that this question is actually only asking us to solve for D, and so there is your solution. And I suppose, to be fair, maybe I should have included units. British pounds. Alright, question number 5. A basketball is dropped vertically. So let me just kind of draw a diagram of the situation. Here's the basketball being dropped, and then it bounces. And on the first bounce, we've been told that it bounced to a height of 2 meters. Let's think of this first bounce as U1, our first term. The basketball then bounces again to 90% of its previous height. You can think of that as U2, where U2 takes our original height but multiplies it by 0.9, representing that it is only 90% of that amount. If you like, you could conclude that that amount is 1.8. That's not really necessary, though. I would probably just leave it as 2 times 0.9. It'll be easier for you to see the pattern. The third term represents the third bounce. And U3, so we take the previous term, which was 2 times 0.9, and then it's got to multiply by 90% of the previous term, because it's only bouncing to 90% of the height. You might notice that this is 2 times 0.9 to the power of 2. Now, if you see what's going on here then, with the third term, we took the original term and multiplied by 0.9 to the power of 2. Look, it's 1 less. Up here, in the second term, we've got our original term of 2 multiplying by 0.9 to the power of 1. Again, the power is 1 less. We can generalize then that on the nth bounce, we'll take our original height of 2, and then we'll multiply it by 0.9 to the power of n minus 1. And it ends up being a geometric sequence. Now the question asks us, what height does it reach on the 8th bounce? So what is U8? Well, that means we've got 2 times, and we're multiplying by 0.9 7 times, right? 1 less, 8 minus 1. Let's put this in the calculator then. So we've got 2 times 0.9 to the power of 7. And we get an answer of, if I round to 3 significant figures, 0.957, and the unit is meters. Alright, I'm going to stop here and continue with another video for number 6 onwards.